Hi everyone, and welcome to this short session today, which is about energy in oscillators. So we've been learning about the equations by which you can predict the motion of something that's oscillating backwards and forwards, like a pendulum on a clock. And we've learned that there are lots of things that we can measure about the pendulum on the clock. We can measure the time period, how many seconds it takes to do a swing. From the time period we could get the frequency, the number of swings per second or complete cycles per second. And we also saw that we could measure the displacement. How far away is it from that central point where the displacement is zero? Also the velocity of the object. The velocity is at maximum here as it races through the middle, slows down, stops, so zero velocity, and then now it's got a negative velocity, it's going in the other direction, and it would reach the same speed, but obviously an opposite velocity, as it swung back through. And because the velocity is changing, we're also interested in acceleration. And from those numbers, we also ended up with a radial frequency, which was omega. And that is the same omega as we use in circular motion for the equations of circular motion. Now what we're going to do today is we're going to take a step forward from these things to talk about the energy in something that is oscillating. And this is quite an important little story because sometimes we want the energy in an oscillating system to be maintained. We want it to keep its energy and not lose it very quickly. And sometimes we do want it to lose its energy very, very fast, and that's called damping when we do this. So let's find out a little bit of the science behind this, and then we'll see some of those contexts. Well, when we do an energy graph for the motion of an oscillating object, whether it's a pendulum or a mass on a spring, then we think about the energy as it varies on either side of the equilibrium point, x equals 0. The displacement is 0 at that point, and we think about the motion of the object and the energy of that object. So let's just think about a very simple form of energy in this, which is kinetic energy. Well, kinetic energy, the thing is stationary at the two extremes. Well, if it's stationary, it has a velocity of 0, therefore by definition kinetic energy must be 0 at the two extremes of motion, at the amplitude on each side. So where is the kinetic energy at a maximum? Well, it's at a maximum where the thing is moving the fastest, which is at that point in the middle. Accelerates, going at a maximum velocity, decelerates, stops, accelerates, maximum velocity, slows down, stops. So at that point there, we have a maximum kinetic energy. And the kinetic energy curve would look like that. So kinetic energy is changing in the system. Well, this kinetic energy may well be changing, but that's because the energy is moving from one form into another form. And in this case, with a pendulum, you may notice that the other form of energy is gravitational potential energy. Look, the pendulum mass, the bob, is higher here than it is here. So it's gained gravitational potential energy. So we could say that as the bob swings from the middle to the amplitude, that kinetic energy is being transferred as gravitational potential energy. So the potential energy of the system is at a maximum at the extremes of the motion and is at a minimum in the middle. Now if we add the two graphs together, we'll see that the total energy remains a constant throughout. So if I just left this system, this is an ideal system in which no energy is being lost from the system, the total energy would remain the same while the energy was being converted between potential energy and kinetic energy. in this story here, we have a mass on a spring or on a spring system oscillating back and forth and back and forth. And as it moved, it would show exactly the same graph. But in this case, it wouldn't be gravitational potential energy that was varying. It would be elastic potential energy. But notice that the situation would be the same in both stories, and the same if I had a mass on a spring that was hung vertically. We might think, oh, this is going to be difficult because here you've got kinetic energy changing, but elastic potential energy and gravitational, it doesn't matter. The potential energy, the total potential energy, would still show this variation, with the kinetic energy being at a maximum as it goes through the middle, zero kinetic energy at those outer points where it stops and starts coming back towards the middle. So we see this energy diagram. Now, let's just talk for a minute about two situations, one in which we would want the energy to dissipate very slowly and one in which we do want it to dissipate quite quickly. Well, a story in which we use the oscillation of an object, say to keep time, might be the pendulum of a clock. So if I had a clock, here's my little Dewberry clock, and this clock was working on a pendulum, swinging back and forth, and the pendulum of the clock helps the clock to keep time. The pendulum is actually driven, is pushed along by the spring mechanism in a clock. But because pendulums show very constant time periods, that's why we use them in clocks to keep time. And in this case, we would want the energy of the oscillating pendulum to not be lost over time. But it would be, wouldn't it? There would be friction in the clock. There would be air resistance acting on the pendulum, and slowly, if I left it over time, that pendulum would slow down and stop and would end up just hanging in the middle, and the clock would stop. So energy would dissipate. This flat line across the top saying that the total energy remains constant and nothing's being lost from the system, that would have to be an ideal system. And there are no ideal systems in physics because it would contradict the second law of thermodynamics for a start. In the end, the energy would dissipate and go out into the surroundings. A situation in which we may want the energy to dissipate quite quickly are situations such as car suspension. So in a car where you've got the front and you've got the wheel arch there, and there's the wheel, and the wheel itself is connected to the car via a suspension system. Now, if the car were going along the road in Newham, where we like a lot of speed humps in Newham, so here's a speed hump, and the car hits the speed hump, that the car would start oscillating up and down, bounce, 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 as the kinetic energy of the car went in and out of the potential energy of the springs. Well, that would be really uncomfortable if you were in a car and that were happening, because every time you went over a speed hump, the car would go bounce, 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 bounce. And cars don't do that. So you have a device that damps the oscillation and takes the energy away from the oscillation very, very quickly. And those devices are called the shock absorbers in the car. They remove the energy of the system so the car goes bounce once and then carries on straight. Well, it does if you have a nice car. And it makes the ride in the car much more comfortable. And we call this, when energy is removed from an oscillating system, we call this damping. And damping is sometimes very useful, like in car suspension, sometimes less useful and you want to minimise it, but we can exploit it to help oscillating systems in engineering. So this story of energy and this energy graph is what we're looking at in today's lesson.